Hey chemists, here we go with mole conversions. This time we're going to go from molecules to moles and from moles back to molecules. Super exciting stuff here. We are going to use your favorite of all numbers, Avogadro's number. So there's Mr. Levitt down in the right hand corner, and check out the mole in my lab coat in the upper left. Avogadro's number, if you don't remember because we haven't talked about it 27 zillion times a day, every day, is the molar mass of a pure substance, and it is 602 sextillion atoms or molecules. It's a counting number, it's a massive number, and because it's so large, we put it in scientific notation. You know this because we've been talking about this for a minute now, right? 6.02 times 10 to the 23rd. That's the number we're going to use for all the conversions we're making today. All right, so if we're going from moles to molecules, we're going to set up a picket fence, if you like a picket fence, and you're going to put what you're starting with in the top left corner, and you're going to make sure that you put Avogadro's number in your picket fence so that the units cancel. So if we're going from moles to molecules, we're going to put Avogadro's number on top. And if we are going from molecules, no, that doesn't want to let me write on it. Here we go, on top. And if we're going from molecules to moles, we're going to go ahead and put that number on the bottom. And so let's take a look at how these work by doing a few together. The conversion, remember, is 6.02 times 10 to the 23rd molecules, atoms, ions, donuts, popcorns, sodas, Swedish fish, you know, whatever. But 6.02 times 10 to the 23rd of them, that's a mole. Here we go. How many molecules are in 0.3 moles of fluorine? So if I'm looking at the fluoride molecule, F2, how many molecules are in 0.3 moles of that? Well, you see the picket fence. Let's get this pen going. So here's the picket fence. Giddy up if you're a picket fence aficionado. And we're going to put our given quantity, our 0.3 moles of F2, all of that goes in the top left. So we don't want to draw on there. So 0.3 moles of F2, all of that is in the top left corner of our picket fence. Alternately, if you are not a picket fence person, you can say times and draw a line, okay? And then you can put your conversion on this next line. If you do that, you want to always remember to put your given over 1, okay? So 0.3 moles of the fluoride molecule times 6.02 times 10 to the 23rd molecules is a mole, right? And when I do that in my calculator, I get 1.806 molecules of F2. But let's go way back to the beginning of the year and recall there was this thing called sig figs. And so leading zeros never count, right? But this 3 is significant. And because there's a decimal point, this 0 to the right of the 3 is significant. So I have 2 significant figures here. So I'm going to count in my answer 1, 2. I'm going to use that third one to see if it rounds. It does not. So I have 1.8, that's an 8, that's a beautiful 8, molecules, it's also a beautiful M, of F2, fluoride molecule. There you go. That's how it's done. Let's do another. Fun times. How many molecules are in 2.9 moles of ammonia, NH3? All right. Jumping into there, 29 or 2.9. Wow. 2.9 moles of NH3. We're going to pretend that that bad boy is right down there in there, right? So, moles to molecules. I'm going to put my conversion factor on top, 6.02 times 10 to the 23rd molecules of ammonia, NH3, the junk you clean with that smells really bad, is equal to 1 mole. And if I do that in my calculator, I get 1.7458, that's an 8. My stylus does not like to draw 8s, times 10 to the 24th molecules. Again, looking back for significant digits, I need to say I report my answer in 2 digits. So 1, 2. Does this 4 round the 7? It does not. So my answer is 1.7 times 10 to the 24th molecules, that's a 4, kids, of ammonia. All right, let's go in the opposite direction. Let's go from molecules to moles. How many moles are in 3.5 times 10 to the 24th molecules of water, H2O? So I'm going to start with my given quantity, 3.5 times 10 to the 24th molecules of water. And I want to know how many moles. So I know that 1 mole of water is equal to 6.02 times 10 to the 23rd molecules, and I'm going to say molec, I'm going to abbreviate that this time, of water. And so if I put that in my calculator, 3.5 times 10 to the 24th divided by 6.02 times 10 to the 23rd, I get 5.8. Well, that comes out nice. I don't even need to worry about sig figs. I need 2, I got 2. That is 5.8 moles of water, H2O. Notice I'm putting a box around my answers. If you ever do these on paper, it's always great to put a box around your answers so your chemistry teacher can find the answer. Okay, last one. How many moles are in 5.7 times 10 to the 25th molecules of potassium iodide? See me cheering up there in the corner? I'm like, woohoo, last one, Ki, let's go. All right, here we go. 5.7 times 10 to the 25th molecules of Ki. And we know 1 mole of potassium iodide contains 6.02 times 10 to the 23rd molecules. And again, I'm going to just write molec here because my stylus today is on the wonky bus. So molecules of Ki, and putting that in my calculator, 5.7 times 10 to the 25th divided by 6.02 times 10 to the 23rd, I get 95.5 and a bunch of stuff moles of Ki. But again, let's look up. And once again, I only need 2 significant digits. Does this 5 round the second number? It does. So in this case, we're going to round up, and our answer is 96 moles of potassium iodide. Put my handy dandy box around that, and we are good to go. Next thing you're going to learn is how to put it all together and do some two-step problems, and it only gets better from there. Welcome to chemistry as math. Later.